uh, sparse subspace clustering handles noisy data and also relaxes the independence condition. Independence condition was that dimension of sum of these subspaces is the sum of dimension of subspaces, and the rank of x was the sum of rank of xi, so we can relax this more. And because we are talking about how well we are clustering, because sometimes, for example, this is one subspace, this is another subspace, and this theta is so small that cluster A is combined with cluster B, so we cannot distinguish between those two clusters very well, and that is the motivation for the concept of incoherence. Incoherence mu I is the maximum of cosine of these principal angles between subspaces. And in radius of polytope xi is another concept that I will explain. I mean, because they have geometric intuition. For example, in a subspace that we have some points and we have a polytope around that. So x could be written as a, x is so this is x, is in lies on convex hull of it. So x could be written as xj cj. And if we just have another point here, let's say x, and we take the polytope and make it bigger and bigger. So make it bigger, it doesn't fit that, making bigger, and finally it fits that. So we want to see if other clusters, probably in different planes, which of them can do this faster. And this is geometric intuition behind that. You know, we have x is xl, this is in polytope L, and some other points are in another cluster, for example, in another subspace. So, I mean, corresponds to polytope which is not L, and we say minus L. And x is equal to, you write x in terms of other points, so x times CL, C minus L. So there is a competition between points in my own group, this is my own group L, and points in other groups minus L. And that is the concept of in radius. So if we have a subspace, a polytope here, and then this is the radius, Ri. Whereas if we have another subspace, and so it's a competition, you know, which subspace can represent it better and easier with less norm. And here, for example, you have some other polytope, but now you have just these 2 points. So this cannot grow faster than the other one. So it reaches, in order to reach x, because it is, the distribution of the points is highly skewed, so it takes time, and so this is the winner. In this case, you know that what should be the angle between those subspaces. For example, this angle this angle should not be too small. It should be very big. For example, this is the best angle that you can write in terms of. So these two subspaces are orthogonal, and this is good. I mean, cluster A and cluster B are well separated, and you have achieved your goal. I mean, the best ideal clustering, subspace clustering. So even if we have a noisy, very, very noisy data, then signal and noise are well separated, and you have achieved a good subspace clustering. And the reason that I defined in radius and also in coherence, mu, was that all of the things that I mentioned are summarized in the theorem, that if the subspaces are sufficiently separated, and the data are well distributed inside the subspaces, then C is a subspace sparse if for all I from 1 to n you're in coherence. This is in coherence, which is maximum of cosine of principal angles. It should be less than in radius. So that one should be less than in radius. So if theta is 90 degree, this becomes 0, and 0 is less than Ri. So it's good subspace separation. So for example, you have a subspace, but you have two more subspaces, and they form a polytope. But this one, the angle between these two subspaces are 90 degree here. But imagine now that they are very close. I mean, the angle between two subspaces is very small, for example 10 degree, and then you cannot distinguish between them. So if angle reduces, there is more chance to fail. That was the geometric intuition behind that. But let's just rewrite a matrix form. Let's see how can we solve this problem that we want to minimize subject to y is equal to yc. You know, the lasso problem is the same, because now you want to minimize L2 norm plus lambda x1, and here this is your yc. So x is now c, this is y, yc is equal to y, so this is y. So in order to solve this efficiently, we use ADMM, alternating direction method of multiplier, to solve the lasso problem. And I will explain it in future lectures. But it's so simple because ADMM method is just you try to form that this x is z, just introduce z as a new variable and subject to xz is equal to 0. That's make it more we can use these ideas to distribute our optimization into different set of machines in a cluster. I mean computer cluster. And then the solution is thanks to Stephen Boyd, I think, that introduced these methods. So the solution is so easy. A transpose B plus rho, our new variable is Z, and update for xk plus 1 plus yk rho, and then your y. Update. So finally they share their variables and talk to each other that, hey, x is equal to z. There are single things. There are single solution. So they communicate. So it's like collaborative filtering. And okay, so let's talk about ADMM in more detail. In more detail, I can say that we want to minimize ax minus b squared plus lambda x, and this is equivalent to saying that we want to minimize exactly this term, but plus lambda z, but subject to x minus z is equal to 0. And we form the augmented Lagrangian. Augmented Lagrangian is the generalization Lagrangian. You add a penalty in that's called augmented Lagrangian. And so this time your Lagrangian this is your f of x. You know, the idea is that you want to separate the variables g of x and g, and subject to x and z, subject to h of x and z is equal to 0. Plus lambda z, this is g of z, so variables are well separated. And then you add your Lagrangian multiplier. This is your Lagrangian multiplier. Lagrangian multiplier times x minus z, plus now you add your augmented Lagrangian multiplier, which is rho over 2 x minus z squared. And this is your h. So ADMM tries to first calculate x bar, which is argmean of this augmented Lagrangian, but this time over x. So y and z are fixed. After that, of course, the solution to this is very easy because xk is just a transpose a plus rho I minus 1, a transpose b plus rho zk minus uk. And the second step is that you now minimize this augmented Lagrangian over z. Now x and y is fixed. And the solution is very easy. The solution is zk plus 1 is equal to s, which is soft thresholding function, s lambda over rho, xk plus 1 plus uk. And finally, we solve this y bar, which is y plus rho h x bar and z bar. And about soft thresholding, I should say, you know, this is just the argmean of 1 over 2 x minus u squared plus lambda L1 norm. And it looks like this. It looks like this. This is lambda, this is minus lambda. This is soft thresholding. S stands for soft thresholding function, which we write it as u minus lambda plus, because here it doesn't go less than 0. And still not practical, because inverting this matrix is hard for large matrices, but we use it different. So it's a distributed ADMM. We use distributed ADMM, and we have to solve this lasso n times. So we have n points. That's why we have to solve this AX equal to B n times. And there are ideas in ADMM to be distributed. One of them is that you use consensus. For example, on machine one, you want to minimize A1 x1 minus y1. So the idea is that A you separate it into 2, and y you separate it into 2, and then you solve this on machine 1, on computer 1, a2 x2 minus y2. Of course, this is constant. On machine 1 it is constant. So you have simplified it a lot. Plus rho x1 minus x2 squared. But on machine 2, we minimize a1 x1 minus y1 squared. But now on machine 2, this is constant and minimize over x2, so we just minimize the second term. Squared plus lambda transpose x1 minus x2 plus rho x1 minus x2 squared. And finally we communicate. We say that, hey, xa is x2. They are equal. So you have to update it. So the machines talk to each other and say, okay, lambda is rho x1 minus x2, and when this term vanishes, then lambda is the fixed point. Lambda converges to its fixed points, and so the relation between this idea and the sketching idea is that we are implicitly doing a kind of sketch. So your sketch matrix is now I n by n 0, but it is a very naive sketch. It's not a good sketch because there is no interaction. And then I n by n, so S1A is equal to A1. S2A is equal to A2. So these are simplified matrices. So instead of A, we have S1A. Instead of S2A. So that is the relationship between ADMM and sketching that very few people talk about it. It's very interesting that ADMM is doing the sketching in an implicit way. It doesn't say, hey, I'm doing sketching. But the kind of sketch, the kind of matrix that it uses for sketching is very naive. You know, here we don't see any interactions between two subspaces. And that's why it can be, I mean, the theory of ADMM can also be generalized. But I don't know if Stephen Boyd has worked on that. So now I want to say, okay, we have calculated these, we have calculated C, and we have found that it is an n by n matrix. And now we calculate this affinity, which is C plus C transpose, to make it symmetric. So we used ADMM. Using ADMM, we solved this. And now you have W matrix, and you can use it for, you have your W is the